Hello everyone and welcome back to another minute concept, this time an in-depth concept about problems involving work-energy relations. So in the last few videos, we were able to discuss that work is equal to the change in kinetic energy as well as the negative change in potential energy. Now we also know that regarding these two types of energy, they are always conserved due to the law of the conservation of energy, wherein the conservation of mechanical energy specifically is described as KE initial plus PE initial is equal to KE final plus PE final. So we know that these two must always be equal at any time, and at any point, adding these two together will get you the total mechanical energy. This is the conservation of mechanical energy. And today, we're going to try questions involving work and this law in order to solve for different values such as velocity, mass, and height, for example. So I have two questions here today and we're going to go through them step by step. So let's just keep these two formulas here in our back pocket so that we can have a guide throughout the questions. So without further ado, let's get into the first one. So again, here are our formulas. Rather. Okay, so a car with mass 1200 kilograms is initially at rest, and it is subjected to a constant net force of 300 newtons in the direction of motion. The force acts over a distance of 50 meters along a straight road. Calculate the final velocity of the car after this force is applied. Now, from here, we can see that we're dealing with a work problem. How do we know this? So the first thing to do is to analyze. What exactly is the question stating? What is it trying to tell you? So it says here that there's a force acting in the direction of motion. Now we were able to discuss in the past few videos that work is when a force is applied or a force is going in the same direction as displacement. So since we're told here explicitly that it's going in the direction of motion, we should start thinking, maybe there is work involved. Now let's try first, before we get to that, listing our given. So our given right now is mass. We have 1200 kilograms here. And then we also have the net force, which is 300 newtons. Or rather, this shouldn't be N, this should be A, because this is a force applied. And then we also have the displacement, which is 50 meters. And we're looking for final velocity. So from here, where do we go? Now, we already know that work is going to be involved here. And work is again described as FD cosine theta. And we also know that work is equal to KE and negative PE. So let's just restate it in this format so that we don't get confused. Or rather, so that it's easier to read. Okay, there. Okay, so from here, now that we know that there's work done, we can actually calculate for that using FD cosine theta. Now we know that cosine theta here is going to be equal to 1, just because the question states that it's a straight road. So that means it's not angled, and the angle here is going to be 0. And cosine 0 is 1, so we're just going to be dealing with force times displacement. So let's try putting force times displacement. So here, we'll put here our net force, which is 300 newtons, and we'll multiply this by our displacement, which is 50 meters, and from here we'll get 15,000 joules. Alright, so now where do we go from here? We are describing the object's the motion of the object, particularly the final velocity of the object after the force is applied, and we have our work done. So what can we relate to work that has final velocity involved, or just simply velocity involved? That is KE, because kinetic energy describes the energy of an object as it's moving. So we also know that work here is equal to delta KE, or the change in KE. So we can now describe our equation as this. Allow me to use the blue and the purple. So we know that work is equal to FD, and we also know that this should be equal to the change in KE, which is described as KE final minus initial. And this is also equal to the delta KE. Now from this, we know that delta KE or KEF minus KEI can be written as the 1/2 mv squared version, or that equivalent, that equation. So we're going to use that same version as in the proof in the last video, and we're going to solve from there. So simplifying the left side, you know that FD is equal to 15,000 joules. So we'll just put 15,000 right here. And the right side should be equal to 1/2 mvf squared minus 1/2 mvi squared. We're not gonna put this anymore. So we know also that according to the question, the object is initially at rest. So mvi squared is just gonna equal 0. So now essentially our working equation is just 15,000 joules is equal to 1/2 mvf squared. So from here, we just have to derive. We're looking for vf squared, or not vf squared, we're looking for vf, so we're just going to isolate it. And how do we do that? We start with multiplying both sides by 2. Now these 2's will cancel out, and we're going to be left with mvf squared is equal to 30,000 joules. 2, 3, 4. Okay, so now after this, we also have our value for mass. So let's add our value for mass into the equation. According to the question, our value for mass is 1,200 kilos. So we're going to plug it in, and we'll get 30,000 joules is equal to 1,200 times vf squared. I'm not going to change pen anymore since we're getting to the same point already. So dividing both sides by 1,200, we'll get 30,000 divided by 1,200 is equal to 25. Or, hold on, yeah, it's equal to 25. So from here, we'll get vf squared, and we're going to get the square root. We'll get 5 is equal to vf squared. So that is how you solve for the final velocity of this object. Alright, so now from here, let's try another question. But before that, let's just recap. Here we use the relation of work and the change in kinetic energy, since we're looking for velocity, and kinetic energy involves velocity. So we related it to KEF minus KEI, and we turned it into its other equivalent. And we know that the object starts at rest, so VI doesn't exist, it's just going to be 0. And we simplified and derived the equation to get 5, oh this shouldn't be squared, 5 meters per second as our final velocity. So now let's go to the second question. Oh, that's from another video. An object with a mass of 3 kilograms is launched from an initial height of 10 meters. As it descends, it reaches a final velocity of 20 meters per second just before hitting the ground. Assuming there is no air resistance, what was the initial velocity of the object when it was launched? Okay, so now we have to start thinking about conservation of energy. We know this because we're talking about an initial height now. And we also know its final velocity right before it hits the ground. And essentially, the question is just asking, what is, if energy should be conserved, it should be the same at the bottom as the top. Because its final velocity is given, it makes sense that we can get the initial velocity at the right before it was at the bottom. Well, yeah, you guys get it. So how do we express this in an equation form? So let's go back to our original conservation of energy formula. So we know that KEI plus PEI should be equal to KEF plus PEF. Now, in the question, it says that we know the value of the object, or the value of the velocity of the object just before hitting the ground. Now, any object just before hitting the ground, let's say for example, right here, like an object with this trajectory, or actually yeah, an object that's dropped straight down, for example. At the top, we know that its potential energy is max and its KE is 0. In the middle, it's exactly half. It's split between the both of them. And at the bottom, PE becomes 0 and KE equals max. In a question like this, it says that right before it hits the ground, its velocity was 20 meters per second. So we know that we're dealing with a maximum here, which is when it's near the bottom or at the bottom. So knowing that, we can also say that PEF here is equal to 0. So our new equation is just KEI plus PEI is equal to KEF plus 0. So that said, we can just remove it. And we know this because of the conservation of energy. So from here, we can actually figure out how to derive for the initial velocity now. So let's recount our formulas. Allow me to get rid of this now. Let's recount our formulas and let's start listing down our given. So beginning first with the given so that we can jump straight into it right after our formulas. Our mass is 3 kg. Our final velocity is 20 meters per second. And our height is equal to 10 meters. And our formulas for KE and PE are, for KE it's 1/2 mv squared. KE is equal to 1/2 mv squared. And PE is equal to mgh. So from here, let's start trying to plug in our values. Let's switch these values into their other formula form. So KEI is equal to 1/2 mvi squared because of the initial plus mghi. Next, we also know that this is equal to 1/2 mvf squared. We have the values of mass, we have the value of gravity, we have the value of height, and we have the value for final velocity. So let's start plugging in our values. So let's use, let's just go purple pen. 1/2 times 3 kilograms times vi squared plus 3 kilos times 9.81 plus plus 10, this should be negative by the way, is equal to, hold on, we're running out of space. This is equal to 1/2 3 kilograms times 20 squared. Okay, so now let's simplify. So we know that this is going to equal 3/2 vi squared plus 3 times negative 9.81 times 10. This is equal to, hold on, minus 294.3, and this will be equal to 400 divided by 2, so 200 times 3, that's 600. Okay, so now we can continue to simplify since we're only left with the variable that we're looking for. So let's go and transpose our 294.3 or our PE initial. So 600 plus 294.3 is equal to 3/2 vi squared. And we're going to simplify even further. This will just become 894.3. Okay, so 894.3. And then we're going to divide both sides by 3/2. So divide by 3/2. Using our calculators, that will get us 894.3 divided by 3/2. Hold up. 3/2. This will get us 596.2. is equal to vi squared. Now again, we just want vi, so we're just going to get the square root of both sides. So the square root of 596.2 is 24.41 meters per second. Or actually, it rounds up to 42, so let's change this to 42. And this is our vi. So that is how we got, let me get rid of this. That is how we get our initial velocity from the equations of conservation of mechanical energy. So just to recap with all of our stuff here, we can use work and its relations to the different types of energy in order to derive our velocity, or essentially other descriptors of the motion of an object. So there's mass, there's well, obviously mass is quite broad, so that question might be a bit difficult, but we can also derive our velocity, we can derive our height. So all of these are related to one another, so they essentially can solve for each other. And it's important to think about the concepts of how kinetic energy and potential energy behave at certain points. Just as I showed earlier, when an object is at the top, potential energy is maxed. When an object is at the bottom, kinetic energy is maxed. So just let that be a guidance for future questions like this. So without further ado, I hope you guys learned something from this video. It's quite short for an in-depth concept, but I hope you guys were able to pick something up. And good luck everyone in any future exams that you have. So thank you everyone, and goodbye.